Hello and welcome to Bringing Back the Oldies, a review of phencyclidine and ketamine analogues, their naming, pharmacology, and EI mass spec interpretation. My name is Danielle St, and today we will be discussing aerocyclohexylamines, their popularity on user forums, and recent analogues found in seized drug samples. Just like vinyl, what's old is new again. Aerocyclohexylamines have been around for over 60 years, and there's been a recent revival of psychedelic research for therapeutic tools, as well as an increase in the availability of gray market analogs. We thought we'd review aerocyclohexylamines, or ACHAs, a subclass of psychedelics known as the dissociative anesthetics. Dissociatives are a class of hallucinogen which distort perception of sight and sound and produce feelings of detachment from the environment or self. Aerocyclohexylamine dissociatives are easily identified by their chemical structure, comprised of three components, including an aryl group, an amine group, and a cyclohexyl group. Phenidates also fall under this definition, but for the purpose of this talk, we will be focusing on those aerocyclohexylamines which connect all three components at the same carbon. The first and most notable aerocyclohexylamine is phencyclidine, or PCP. PCP has a nefarious history. As an example, in 1996, during the filming of the Titanic, during the final days of shooting the film, the crew unknowingly dined on chowder that someone had laced with PCP. This caused mass hysteria and hallucinations and a trip en masse to the ER at 1 in the morning. PCP was discovered by accident at Park Davis in the early 1950s when a Grignard reaction yielded an unexpected product. It was quickly identified as an incredibly potent anesthetic, and what's more, it did not cause cardiac and respiratory depression like the classical anesthetics of the time. The drug was marketed as Cernal, however dissociation, delirium, and long post-op recovery times were observed in some patients, while others experienced agitation and aggression in clinical trials. Because of these side effects, Cernal was then relegated to veterinary medicine. Other analogs were investigated, including eticyclidine, or PCE, which had the same side effects but also caused hallucinations. The phencyclidines were eventually abandoned in favor of ketamine, similar in structure to eticyclidine, but an additional chlorine is added to the aryl group and an additional ketone to the cyclohexyl group. Ketamine was less potent than its phencyclidine counterparts, and exhibited shorter duration time with fewer side effects, making it more ideally suited as an anesthetic. The synthesis of phencyclidines is straightforward via the Methoxetamine route, named for the Park Davis chemist who discovered the reaction. This method combines cyclohexanone, potassium cyanide, and piperidine to form PCC. PCC is then subjected to Grignard conditions to form the final phencyclidine product. This is also the most common method used by clandestine chemists and is known as the bucket method for the three buckets that it is performed in. Bucket 1 contains cyclohexanone and sodium metasulfate, while Bucket 2 contains the piperidine and potassium cyanide. Bucket 1 is poured into Bucket 2, stirred and left to cure overnight to form the PCC, which is filtered and dried, and then subjected to Bucket 3, where the Grignard reagent is prepared by combining magnesium tunings, iodine crystals, and bromobenzene in ether. When the PCC is added, the reaction goes to completion, and the cyanide byproduct is poured off. The final product is then salted with HCl. The enamine and imine routes are also common, following a similar route as the Mannix pathway. The Park Davis route to ketamine is the most popular route as well. There are many ways to form this ketone intermediate through various starting materials. Then it's just a few steps to the final product through a ring expansion step. Some of the most common byproducts that are seen in street samples are PCC analogs and the ketone intermediates. The simplicity of the aerocyclohexylamine structure and the straightforward synthesis with easily accessible starting materials allows for a seemingly endless variety of analogs. An easy way to recognize the structure of these analogs is by recognizing how they are named. Multiple ways to name aerocyclohexylamines, so I've put together a tutorial on some of the most commonly observed naming conventions. These are not so much rules as they are observations. Phencyclidines are typically referred to by their acronym, which appears to come from the aerocyclohexylamine class name. The first letter of the acronym is the aryl group, followed by the C for cyclohexyl, followed by the first letter of the amine group. This may also have come from the original IUPAC name for phencyclidine, and analogs that followed were named based on this format. The actual IUPAC of some of these can be pretty lengthy, which is why it appears to be a pseudo-IUPAC format that is followed. Phencyclidine is called PCP, named for the P of the phenyl group substituent, C for the cyclohexyl core, and then P for piperidine. If the amine substituent is a pyrrolidine, then the P for piperidine is replaced by PY for pyrrolidine. If the amine is substituted with an ethylamine, then E replaces P to make PCE. If the aryl substituent is thiophene, as in tenacyclidine, then the P for phenyl is replaced by T for thiophene to form TCP. If the aryl substituent is a benzothiophene, then the first P is replaced by BT for benzothio, followed by CP to give BTCP, and so on. Substitutions on the aryl group appear before the acronym, as in 3,4-methylene dioxy PCP, abbreviated to 3,4-MD PCP, and so on. There are many ways to name ketamines. It's a little bit more complex, but we're going to go over 3 of the most commonly seen nomenclature systems. My personal preference for naming ketamines uses the PCP nomenclature as the base, while adding the 2-oxo designation between the aryl substituents and the base acronym. 2-keto may also be used, but this is much less common. The oxygen on the cyclohexyl group is located at the 2 position on the cyclohexyl, but if it was at the 4 position, then it would be dubbed 4-oxo or 4-keto instead, and so on. Note that you may or may not see a prime used in the numbering of ketamine, and it may or may not be used interchangeably with the primes on the aryl or on the cyclohexyl group. For simplicity's sake, we'll leave the prime designation off for the purpose of this workshop. Now, if we start with ketamine, when we look at the structure, ketamine has a 2-chlorophenyl group and a methylamine group, which would give us 2-chloropCM if we were naming it through PCP nomenclature. Then we add the 2-oxo group between the aryl substituent and the acronym to give us 2-chloro 2-oxo PCM. The unsubstituted aryl version of ketamine is 2-oxo PCM. However, this compound is commonly known as dischloroketamine on the Gray Web, which we will discuss in a moment. The 2-oxo may also be shortened simply to O to give OPCM. In the case of eticyclodone, we would expect 2-oxo PCE, but it is commonly referred to on Gray websites as OPCE. The second set of nomenclatures we're going to discuss are the deschloro and nor nomenclature systems. When the chloro substituent on the aryl group of ketamine is swapped out for a different substituent or omitted, the deschloro nomenclature is often used. Deschloro means without chlorine. The acronym is D for des, C for chloro, and K for ketamine. If we remove the chlorine from the 2 position and add a bromine at the 3 position of the aryl group on ketamine, we would get 3-bromo-deschloroketamine, or 3-BR-DCK. When the amine is substituted with a group other than methyl, we see nor, which is used to indicate the removal of the methyl group. The new amine substituent will then precede the root norketamine. In the case of the methyl being replaced with an ethyl group, we would see N-ethyl norketamine, or NENK. When both aryl and amine substituents are replaced or changed, The order becomes aryl substituent, followed by deschloro, followed by N, followed by amine substituent, followed by norketamine. If we switch the 2-chloro for a 3-methyl aryl substituent and the methylamine for an ethylamine substituent, we would expect to see 3-methyl deschloro N-ethyl norketamine, or 3-ME-DCNENK. But that's not what it's typically called on illicit websites and user forums, which leads us to the third set of naming conventions, the designer names from user forums. When 3-methoxy deschloro N-ethyl norketamine hit the designer drug scene in 2006, it was marketed as methoxetamine. As a contraction of methoxy and ketamine, it was abbreviated MXE. This nomenclature appears to loosely follow PCP nomenclature using the aryl substituent as the first letter, the amine substituent as the last letter, and X in the center to indicate the 2-oxocyclohexyl group. From what I've seen on the illicit market sites and user forums, most of the aryl substitutions are located in the 3 position of analogs of methoxetamine, while amine groups vary, and we'll discuss why the 3 position is popular shortly. Derivatives of methoxetamine have followed suit with hydroxetamine as HXE, fluoroxetamine as FXE, as well as methoxisopropamine as MXIPR, and methoxpropamine as MXPR. 3-methyl deschloro N-ethyl norketamine takes on the designer methoxetamine core to give deoxymethoxetamine, indicating the removal of the oxygen with a deoxy. Curiously, this substitution is placed in front of MXE. If we go over and recap all of our naming conventions using this structure, we see that with the PCP type naming, we have a 3-methoxy group on our aryl substituent, an N-ethylamine, and a ketone on the cyclohexyl group at the 2 position, which would give us 3-methoxy, 2-oxo, phencyclomethylamine, or 3-methoxy 2-oxo PCM. If we use the DeschloroNomenclature, we can see that this has the ketamine core with the methylamine and the cyclohexyl group with a ketone at the 2 position, but we substituted a methoxy group in the 3 position and omitted the chloro here at the 2 position, which would give us 3-methoxy dischloroketamine. If we use the user forum methoxetamine naming convention, we have methoxetamine, but instead of an ethylamine, there's a methylamine, which would form methoxmetamine, or MXM. You could also use the curious method of showing substitution by placing the M for methylamine in front of MXE, as they did with the D for DMXE. I hope this tutorial has given you a good foundation to recognize the structures of aerocyclohexylamines from their names and abbreviations. And now we're going to get into pharmacology and talk about that 3 position. Aerocyclohexylamines are NMDA receptor non-competitive antagonists, which means that they block the NMDA receptors, and this causes an excessive release of excitatory neurotransmitters into the synapse of neurons. The exact mechanism is still not fully understood, but research continues, and just last year, the binding sites of S-ketamine were elucidated. Despite not understanding the exact mechanism, clinical observations do show that these compounds can be therapeutic in small doses and work quickly for the treatment of depression, especially ketamine can be used as an emergency intervention. Most antidepressants can take weeks to come to full effect, whereas ketamine improves mood and thoughts of well-being within hours. This also explains why there's so much abuse potential. And the dose does make the poison, according to Paracelsus. At higher doses, dissociation, hallucination, mood disorder, and other manifestations of emotional distress have been observed in clinical settings. Now we can revisit the popularity of aryl substitutions at the 3 position of methoxetamine analogs. These modifications go back to user-form discussion in the mid-aughts based on studies that showed opioid binding by 3-hydroxy-PCP. Users postulated that they could get opioid activity by combining elements of 3-hydroxy-PCP with ketamine. Users hypothesized that adding an oxygen substituent to the 3 position on the ketamine backbone would give the drug opioid-like activity. Extending the amine substituent from methylamine to ethylamine would increase the duration of the experience, and the ketamine backbone would make the drug safer than its PCP counterpart. These were all hypothesized by users on user forums, and despite the hypotheses, there is no evidence that these ketamine analogs bind to the opioid receptors. However, NMDA binding studies do show that the 3-methoxy substituents consistently bind with higher affinity compared to their 2 and 4 analog counterparts. NMDAR studies on PCMO analogs by Kohlstock et al. Showed that 3-methoxy PCMO was at least 6 times stronger than its 2 and 4 methoxy substituted counterparts, requiring a concentration of around 400 nanomolar to elicit the same response that took more than 2400 nanomolar by the 2 and 4 methoxy analogs. Roth et al. Also screened a number of ACHAs in 2013. 3-methoxy PCP binds 20 times stronger than 4-methoxy PCP. Methoxetamine fell between PCP and ketamine and is about 2.5 times stronger than ketamine. Methoxetamine was released to market in 2010. On December 7th of last year, the DEA issued a notice of intent to schedule methoxetamine in the United States. In the past couple of years, we've seen several alerts for new aerocyclohexylamines, including 3-chloro-PCP, 3-fluoro-PCP, methoxy-PCE, and methoxypropamine. Included in illicit sites and Reddit chatter are these ketamine and phencyclidine analogues. Some of the highlights include fluoroxetamine, 2-bromo-dischloroketamine, 3-chloro-PCP, 3-methyl-PCP, 3-methyl-PCPY, methoxyisopropamine, methoxypropamine, and deoxymethoxetamine. With the possibility of thousands of analogs, you may be wondering how to begin to identify them all. I've put together a few handouts for you and compiled some tips and tricks for recognizing aerocyclohexylamines in your EI mass spec samples. I'm not an expert in EI mass spec, and there may be better ways, but here are a few trends I've noticed while looking through various spectra. Let's begin with the phencyclidines. With phencyclidines, you will always see the M+ radical ion in your spectra. This will also give you the molecular weight of your compound. There are 3 diagnostic peaks to look out for. The first 2 are these 2 cation structures, the eliminated amine cation on the left and the aryl elimination cation on the right. These 2 structures will always show up together. If you see peaks 84 and 166 together, it is likely that you have a piperidine substituted phencyclidine. Different amines will have different pairs of peaks to look out for, as well as different base peaks. The base peak of your phencyclidine is this aryl aminocation at 200 mass units. Now remember, when you add a substituent to an aryl group, you also have to remove a proton. If you have an aryl substitution, you can identify the substituent by subtracting 200 from your base peak and adding 1. We can simplify it further. Take the base peak of 200, subtract a proton to give 199, and then subtract 199 from your base peak, and that will give you your aryl substituent. These are the common fragment structures of phencyclidines, and you can also find these in your handout. Let's do a quick practice run. Here are the common amine substituted diagnostic peaks you will find. Remember that the amine cation and the aryl elimination cation are always seen together. Look at our spectrum. Do we see any of the combinations? Do we see 84 or 166? How about 58 or 140? Do we see 44 or 126? Do we see 30 or 112? We see 70 and 152. This suggests that we have a pyrrolidine substituted phencyclidine. Next, let's look at the base peak. It's 186. This also coincides with an unsubstituted aryl substituent. The M plus is 229, which is the mass of PCPY. Let's identify a suspected aerocyclohexylamine unknown spectrum together. Here is our spectrum. Let's look for the amine substituent first. Do we see two peaks that go together? I'll give you a few seconds to identify them. I see 84 and 166. That means we have a piperidine. Now we're going to have to identify the aryl substituent. We do this by taking our base peak, subtracting 200 minus H. I'll give you a few seconds to find out what the aryl substituent is. I came up with 35. That gives us a chlorine. That's further confirmed by the 3-to-1 ratios of the peak intensities. Now remember, with aryl substituents, we can't say with certainty what position the substituent is on, just that we have a chlorosubstituted phencyclidine. We see that confirmed by the M plus radical peak at 276. Here are some of the chlorosubstituted phencyclidine fragments that you will encounter. Ketamine fragmentation isn't quite as straightforward, but it still follows some recognizable patterns. For simplicity, we'll go over these patterns with deschloroketamine. The M plus radical of ketamine analogues is often there, but the abundance is very, very low. You will also see peak 77 and 91 for the benzene and tropylium cations. The caveat is that you will not see 77 or 91 if you have a fluorine substituent on the aryl group. You will then see 95 and 109 for the fluorobenzene cation and the fluorotropylium cation. If you see these two sets of peaks, the next thing to look for is a difference of 29 between the base peak and the next largest peak. You will also see typically 14 units lower than the base peak as well. The next thing I look for are the diagnostic peaks, which are the two most common fragments in ketamine. The first is the aryl NH2 iminium ion, and the second is the ethyl benzyl cation radical, found at 104 and 132. The base peak is the R1 N-substituted iminium cation if the aryl group is unsubstituted. If the aryl group is substituted, you'll have to identify both the amine R1 substituent and the aryl R2 substituent. To find the R2 substituent, look for a peak with a mass of difference of 104 minus H, or simply the peak minus 103. If your aryl group is unsubstituted, then the way to find the amine substituent is by taking the unsubstituted iminium ion mass of 132, subtracting a proton to get 131, then subtracting 131 from your base peak. In this case, R1 is 15, which coincides with a methylamine substitution. Using these trends, let's walk through identifying a suspected ketamine unknown. The first things that we want to look at, do we have a base peak with another peak 29 mass units higher? Do we see 91 or 77? Do we see 104? Do we see a possible M plus radical? I'm going to give you 30 seconds to take a look and see what you can find based on all of these trends. Okay, we do see that there is a peak 29 units higher than our base peak, and we also see a peak 14 units lower than our base peak. And we also saw a possible M+ radical at peak 235. Now to find the substitutions. I don't see 104, but is there another peak that we might want to look for? I'll give you 15 seconds to try and identify a peak. We do see a peak at 122. If we subtract 103 from 122, we get 19. That indicates fluorine. We don't see peak 77 or 91, but remember when I said if you have a fluorine substituent, you won't see those, but you will see 95 and 109. Now we know that we have a fluorine as our aero substituent. Since it's a ketamine derivative, we're going to assume that it's in the 3 position for now, based on pharmacology we discussed earlier. But remember, this is just an assumption. Now we need to find out what the amine substituent is. Our base peak is 178. The amine substituent is the base peak subtracting the substituted iminium ion, which comes to 131. And we also have to subtract R2 minus H, because remember, when you add an R2, you have to subtract an H. See if you can find out what the amine substituent is using this calculation. I'll give you 30 seconds. Do you got it? The amine substituent is 78 minus 131 minus 18. That should have given you 29, which gives you an ethylamine substituent. It looks like we have fluoroxetamine. Here are the common fragments that you would anticipate seeing in fluoroxetamine. We'd love to help you identify your unknown. If you go to www.caymanchem.com and click on our Forensics tab, we have a product search and drug identification tool. When you click on that, there's a GC mass spec drug identification tool that will take you to a series of filters. You can input your data and search by analytical standards that we have available, and then find the GC mass spec that we've run from there. If you do not find your unknown, please do send us your GC mass spec data and any relevant information such as the suspected class, the matrix, any solvents and GC parameters that you've used to techserve@caymanchem.com, and we'll try to help you solve your unknown. Here's the list of the most recent MPS we've released in 2020 and 2021. Under the hallucinogens, we have our aerocyclohexylamines that I mentioned to you earlier. I have included the item numbers for you so it's easier for you to identify and find on our website. We've also released pyrethyldione, which is a hypnotic. Several tryptamine analogs were released in this time frame, and we also have a couple of LSD analogs. We've also released several stimulants. The most recent I've seen on the Gray websites is this one with a rather large name. It's being sold as C-Putolone on Gray sites. We also have our benzodiazepine analogs. We have a few meperidine opioid analogs, as well as a new U compound. Continuing with the opioid classes, we have the fentanyl class. There's a few one-pot reaction impurities that have been identified. Parafluorofentanyl has made a comeback. Some of the impurities that are found in those samples include the norfentanyl and anilinopiperidine starting materials and side products. There's also been acylated norfentanyl analogs identified that don't fall under the scheduling by the DEA. We also have the most recent nitazene analogs, the N-piperidinal adenitazene and the N-pyrrolidinal adenitazene. And there's also been chatter on methadone analogs, including dipionone and desmethylmoramid, and those have also been seen on gray websites. Thank you all for attending our workshop this afternoon. I'd also like to thank CFSR EMPS Discovery and our conference organizers and workshop colleagues for inviting us to host this workshop this afternoon, and for all the work that they do in the community. I'd like to thank Cayman Chemical Company and the Forensic Chemistry Division. It really does take a village. We work with a great group of scientists. They all help with the publications and the tools and the NPS standards that we make from synthesis to QC. I'd also like to especially thank Holly Pierzynski and Roxanne Frankowski for their assistance with the EI Mass Spec portion of this workshop this afternoon. And I'd also like to thank Don Ayula, our VP of Forensic Chemistry, who's always encouraging us to go out into the community and present our hard work, and is always our cheerleader and always trying to make a difference in the community. So you can sign up to receive email notifications on our new standards, tools, and publications if you go to www.caymanchem.com and register. You can also follow us on Twitter at Cayman_forensic and Facebook or LinkedIn. And if you need additional help, don't hesitate to reach out. You can email me directly at dstgermaine@caymanchem.com, or you can reach out to tech support at techserve@caymanchem.com. So please don't hesitate to reach out.